In the last video, we took a look at doing momentum conservation in 2 dimensions. Here we're going to go and take a look at the rotational version of this called angular momentum. So you can, in total analogy to what we've done with forces and torques, you can take the definition of translational momentum and extend it into an angular version. And in the specific case where an object is rotating about its long or short symmetry axis, which turns out to be an awful lot of cases, the angular momentum, that's this capital L here, can be set equal to the moment of inertia times the angular velocity. And the units of this are kilogram meters squared per second. Now, just to show you that there is a little bit more under the hood here. If you want to try this at home, find yourself a box, like a box of tissues works great, especially if they haven't been opened yet. But you need a box where all the lengths of the 3 lengths of the box are all different. And like I was saying, if you spin, this relation works if you spin along the long axis like this, and you spin along the short axis like this. And if you actually take your box and spin it around those axes, you'll find that they spin very stably. So I'll just say stable and stable. But if you try tossing it about this axis that's intermediate in the length of the 2, you'll find that it's unstable. By that I mean you'll notice that the box tumbles. Now, the strange bit is during this tumbling, the angular momentum doesn't actually change. And so to do this, we have to do a more complicated treatment that's in the same spirit as what we have here, but it's beyond the scope of what we're doing. But still, it's fun to check out. So, take that box of tissues, spin it the long way, spin it the short way, and then spin it the middle way, and you'll see that the middle way tumbles no matter what you try. Okay, and so with that, it turns out that much like when what Newton actually said in his second law was that the net force is equal to the time rate of change of momentum of an object, Newton's second law for rotations Newton's second law for rotations can be written as the net torque applied to an object is equal to its time rate of change of angular momentum. And we'll work through a numerical example of this and do some demonstrations. So we'll start here by observing that just like when conserving the translational momentum, if the system is isolated, so here what we're saying is if the net torque on the object is 0. So this doesn't necessarily require the net force to be 0, but if the net torque on the object is 0, or on the system is 0, then that means that the change in momentum with respect to time has to be 0, but then that means that the momentum never changes. So we can write that if the net torque is equal to 0, the final angular momentum has to equal the initial angular momentum. So to make a concrete example of that, let's say that you are looking down at a table So this is the surface of the table you are looking down at from above. Let's say someone's drilled a hole into this table right here. And what you're going to do is you're going to lay a washer flat on the table. Oops, I need my washer to be a little bigger, a little smaller, I mean. So let's say you laid a washer on the table right here. And you tied a string around that washer and fed it in to the hole. Now underneath, after we get this washer spinning around, you're going to have somebody pull down on the string. So initially, though, we just get the washer moving around. And let's say it's moving around at a initial radius here of, let's say, 1 meter, going at an initial angular velocity of 10 radians per second. Now, you go and pull on the string, or have your friend do it, or whatever. So eventually that washer gets closer to the hole, and it's going around a circle like this. And let's say the final radius is 0.5 meter. What we would like to know is what is the final angular velocity. And yes, I know that should say initial there. There we go. Now, at first, you might say, hey, this seems totally unfair. After all, we have no idea how to characterize the force the string was exerting, and then a person's pulling on the string. We've got no clue. But here's the trick. The trick is that we can make this our axis of rotation. Now, the force due to tension in the string will always be directed in a line that goes through that axis, right? So that means this lever arm is 0, and so the torque is 0. Because the torque on this system is 0, we can write that the final angular momentum is equal to the initial angular momentum. So this will be the final moment of inertia times the initial. Keep in mind, since this moved in, it's going to have a smaller moment of inertia. So I final omega final will have to equal whatever the moment of inertia times the angular velocity was before. So we can write that omega final is I initial I over I final omega initial. Now we can, if the washer is small, these distances are big, we can well approximate this washer as a point mass. And if we look up the moment of inertia of a point mass going around in a circle, it turns out to be the mass of the object times the square of the radius of its orbit. And so that's my omega, my I initial. Here's my I final. And there's omega initial. So the mass of the washer cancels out. Good thing, since I never gave it to you. And we can now go ahead and stick in the numbers. So we can clean up just a shade. R initial over R final squared omega initial. Now let's put in the numbers. 1 meter over 0.5 meter squared times 10 rad per second. Well, 1 meter over 0.5 meter, that's just the number 2. Squared is 4. And so they'll be spinning around 4 times as fast at 40 radians per second. In this demo, I'm holding 2 weights out at the ends of my arms try to predict what will happen to my angular velocity as I bring the weights in. So here, when I brought the weights close to my body, I decreased my moment of inertia. Because there were no external torques on the me plus weights system, when the moment of inertia went down, the angular velocity had to go up in order to keep the angular momentum the same. In the remaining demos, I'm going to be using this thing that looks like a bike wheel, except that what looks like a tire is actually a rather heavy copper cable, so the thing has a very large moment of inertia. Predict what will happen to me when I give the wheel a spin. By giving the wheel a spin counterclockwise when viewed from above, I gave it positive angular momentum. Because me and the wheel are an isolated system, I had to have exactly the same amount of angular momentum, but negative, in order for it to cancel out to zero. Therefore, I spun the other way. This is actually the principle behind reaction wheels used in satellites in order to point them wherever they need to be pointed. In this demo, I'm going to spin the wheel, then get on the turntable, and then stop the wheel with my hand. Predict what will happen next. Since the wheel plus me system was isolated, when I stopped the wheel, its angular momentum dropped to zero, but the angular momentum of the system had to remain the same. Therefore, I rotated as a result. And finally, I'm going to spin the wheel, then get on the turntable, then flip the wheel upside down, and then flip it back right side up. Predict what will happen next. When I flipped the wheel upside down, I changed it from having a positive angular momentum to a negative angular momentum. However, the wheel plus me system had to remain a constant. As a result, I had to pick up 2 times the original angular momentum in order to keep the angular momentum of the wheel plus me system the same. As a result, I spun the way the wheel was originally going. When I flipped the wheel back right side up, I once again restored it to where it was before, and my angular momentum could drop to zero.